Hello, today we're going to talk about representations of equilibrium. Okay, so here's an example of a particle representation of equilibrium. So we have our reaction A2 plus 3B2 yields 2AB3. So you can have these particle representations of them. So the system is initially at equilibrium, and then some AB3 is added. So this is going to be our A2, this is going to be our B2, and this is our AB3. Then the reaction moves to a new equilibrium. So when we go through this first step, we still have the same amount of A2, okay? And we also still have the same amount of B2, but we just have more AB3, right? And it looks like we added 4 new molecules of AB3. So it's not at equilibrium anymore because we added some extra product. Because we added some extra product, the reaction is going to proceed in the reverse direction to reestablish equilibrium. So I need to use up some of those AB3 molecules. Well, if I do the reverse reaction one time, I will use up two of the AB3 molecules and create create one more A2 molecule and 3 more B2 molecules because of the stoichiometry of our reactant side. So we're left with 5 of the AB3s because I used up 2 of the new ones. I had 3 A2s to begin with, and I added an extra one, so now I have 4. And then I had, let's see, 1, 2, 3, 4, 5. I had 6 B2s to begin with, and I added 3, so now I'm up to 9. So when you're drawing these representations, you really just need to make sure that you're counting the particles before and after. You also need to make sure that you're following the stoichiometry of the reaction. So if you're paying attention to the coefficients. And then finally, you want to pay attention to the states. So all of these are aqueous. That means they're dissolving in water. We assume these are, containers full of water, so they're spread out throughout the container. You would do the same thing if you were doing gases. But if you have any liquids or solids, you want them to sink to the bottom of the container. But remember, liquids and solids don't affect the position of your equilibrium. Okay, so you could also use that same example from the previous slide, but graph the amounts of each substance over time. So originally we had some A2, and then when we added AB3, we proceeded in the reverse reaction and created more A2. Originally we had some B2, and when we added AB3, it proceeded in the reverse direction, and it created more B2. But notice how the B2 increased by a lot more than the A2, and that's because the reaction was A2 plus 3B2, right? So it's going to increase 3 times as much as the A2 if it's proceeding in the reverse direction. So 2AB3. And then for the AB3 itself, we started at equilibrium, and then we added some AB3 in. Okay, so it suddenly and very rapidly increased its amount. And then we wanted to use some of that excess up, so we used up 2 of those extra AB3s, so that's why you'll see it's decreasing. And if you pay attention, it decreases, the amount it decreases is twice as much as the amount A2 increases because of the stoichiometry, the 1-to-2 relationship there. Okay, so we have this example. It's a little long, so we're just going to do one example. We've got A 3 plus B minus yields AB2 plus, all aqueous. So we have 1 liter of water. There's 1 mole of A, 4 moles of B, and 8 moles of AB. And what is the value for the equilibrium constant? Well, to solve that, we're just going to use some strategies from the previous sections. We're going to write our equilibrium constant first, our expression first, AB 2 plus on the top, 3 plus and B minus on the bottom, and then we're going to plug in our values. Now we want to plug in molarity, but fortunately they gave us moles and it's 1 liter, so 1 over 1 is just 1, and 4 over 1 is just 4, and 8 over 1 is just 8. So we can solve very quickly and easily. That's our equilibrium constant is 2. Okay. Draw an image to represent this initial state. So let's go ahead and draw our container. We're going to assume it's filled with water. And then we have 1 mole of A. I'll use green for A. So just 1 mole of that. We have 4 moles of B, blue. And then 8 moles of AB. So I'm going to use purple for that. I know we're combining them together, but it's going to actually use red. It's going to be easier for me to draw just in a different color. 1, 2, 3, 4, 5, 6, 7, 8. So there is our equilibrium mixture that they told us about. And at some time t, we add 13 moles of AbCl2, and the volume change is negligible. The change in volume could affect the molarity, so a lot of times you'll see that the volume change is negligible. That's just makes the calculations easier. So AbCl2 is a completely soluble compound that forms Ab2+ and 2Cl negative ions, and the chloride ions are spectator ions. They don't affect the equilibrium, you do not have to include them. So essentially we're adding 13 moles of Ab2. It's just a lot of extra words to mean that. Draw 2 models to represent this occurrence, one for the instance the substance was added, and one to show the reaction reestablishing the equilibrium. All right, so let's draw our new container. I'm going to draw it a little bigger just so I have space. Okay, so the instance that was added, we still have just 1 A, and we still have 4 of the B, and our initial 8 AB2s, and then the instant time t, 13 moles was added. So I'm going to add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So a lot more molecules now. And then we need to show that the reaction is reestablishing equilibrium. Okay. So we need to use up some of that excess product that was formed, so I'm going to shift the reaction towards the reactant side. So I'm going to go in the reverse direction. And if I were to perform that reverse reaction just once, one of the AB2s will get used up, and we will form an extra A, and we will form an extra B. So that means in our equilibrium system, we will have now 2 of the A's. We will now have 5 of the B's. And we'll go down to just 20. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Just 20 of the AB's. And if you wanted to check, you can plug those values back into your equilibrium expression. So now we're at 20 for our AB2 molecules. We are at 2 for the A molecules and 5 for the B molecules. And 20 over 10 is equal to 2. And so you can just do some trial and error until you get back to that equilibrium constant value. So I only had to do that reverse reaction once to get it to reach 2 again, but you can do it a second time or a third time or a fourth time using up some of the products each time.